Force and Laws of Motion of Class 9 Science NCERT. I hope the screen is visible to everybody. Let's begin with the reading. So here it is. In the previous chapter, we described the motion of an object along a straight line in terms of its position, velocity, acceleration. We saw that such a motion can be uniform or non-uniform. We have not yet discovered what causes the motion. Why does the speed of an object change with time? Do all motions require a cause? If so, what is the nature of this cause? In this chapter, we shall make an attempt to quench all such curiosities. For many centuries, the problem of motion and its causes had puzzled scientists and philosophers. A ball on the ground, when given a small hit, does not move forever. Such observations suggest that rest is the natural state of an object. This remained the belief until Galileo Galilei and Isaac Newton developed an entirely different approach to understand the motion. So here in this figure 8.1, it is being written pushing, pulling or hitting objects change their state of motion. So we come on to the right side of this page. In our everyday life, we observe that some effort is required to put a stationary object into motion or to stop a moving object. We ordinarily experience this as a muscular effort and say that we must push or hit or pull on an object to change its state of motion. The concept of force is based on its push, hit, or pull. Let us now ponder about a force. What is it? In fact, no one has seen, tasted, or felt a force. However, we always see or feel the effect of a force. It can only be explained by describing what happens when a force is applied to an object. Pushing, hitting, and pulling of objects are all ways of bringing objects in motion, figure 8.1. They move because we make a force act on them. From your studies in earlier classes, you are also familiar with the fact that a force can be used to change the magnitude of velocity of an object, that is, to make the object move faster or slower, or to change its direction of motion. We also know that a force can change the shape and size of objects as seen in figure 8.2. So figure 8.2a is showing a spring expands on application of force and B is showing a spherical rubber ball becomes oblong as we apply force on it. So we are done with the reading of this page. We are coming to the next page, and this page is 88, and this is the left side that we will be reading it first. So next topic is 8.1, balanced and unbalanced forces. Figure 8.3 shows a wooden block on a horizontal table. Two strings X and Y are tied to two opposite faces of the block as shown. If we apply a force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But if the block is pulled from both the sides with equal forces, the block will not move. Such forces are called balance forces and do not change the state of rest or of motion of an object. Now let us consider a situation in which two opposite forces of different magnitudes pull the block. In this case, the block would begin to move in the direction of the greater force. Thus, the two forces are not balanced and the imbalanced force acts in the direction and the block moves. This suggests that an unbalanced force acting on an object brings it in motion. Figure 8.3, the forces acting on a wooden block. What happens when some children try to push a box on a rough floor? If we push the So here we come to the right side of this page. Box with a small force. The box does not move because of friction acting in a direction opposite to the force. Figure 8.4a. This friction force arises between two surfaces in contact, in this case between the button of the box and floor's rough surface. It balances the pushing force and therefore the box does not move. In figure 8.4b, the children push the box harder but the box still does not move. This is because the friction force still balances the pushing force. If the children push the box harder still, the pushing force becomes bigger than the friction force. Figure 8.4c. This is an unbalanced force, so the box starts moving. What happens when we ride a bicycle? When we stop pedaling, the bicycle begins to slow down. This is again because of the frictional forces acting opposite to the direction of the motion. In order to keep the bicycle moving, we have to start pedaling again. It just appears that an object maintains its motion under the continuous application of an unbalanced force. However, it is quite incorrect. An object moves with a uniform velocity when the pushing force and frictional force acting on the object are balanced and there is no net external force on it. If an unbalanced force Hi Ayush Shukla, this is just an audiobook, so this is not an explanatory video. I am just reading out the book. I hope the screen is visible. However, it is quite incorrect. An object moves with a uniform velocity when the forces, pushing force and frictional force acting on the object are balanced and there is no net external force on it. If an unbalanced force is applied on the object, there will be a change either in its speed or in the direction of its motion. Thus, to accelerate the motion of the object, an unbalanced force is required, and the change in its speed for in the direction of motion would continue as long as this unbalanced force is applied. However, if this force is removed completely, the object would continue to move with the velocity it has acquired till then. So 8.2 First law of motion. By observing the motion of objects on an inclined plane, Galileo deduced that objects move with a constant speed when no force acts on them. He observed that when a marble rolls down an inclined path, its velocity increases, figure 8.5a. Ayush Shukla, please don't send angry emojis. This is the English reading of NCRT of grade 9. So next time when I will be recording Hindi, at that time you can join. Thank you for now. In the next chapter, you will learn that the marble falls under the balance force of gravity as it rolls down and attains a definite velocity by the time it reaches the bottom. Its velocity decreases when it climbs up as shown in figure 8.5b, 8.5c shows the marble resting on an idle frictionless plane inclined on both sides. Galileo argued that when the marble is released from left, it would roll down the slope and up the opposite side to the same height from which it was released. If the inclinations of the plane on both the sides are equal, then the marble will climb the same distance than it covered while rolling down. Good morning, Ayush. So we are here. If the angle of inclination, just wait. If the, where were we? So if the inclinations of the plane on both the sides are equal, then the marble will climb the same distance that it covered while rolling down. Just wait. Just wait a second. Let me make the settings proper and then we'll start. So here it is okay now. If the angle of inclination of the right side, I think there is some problem here. If the inclination of the planes on both the sides are equal, then the marble will climb the same distance that it covered while rolling down. If the angle of inclination of the right side plane were gradually decreased, then the marble would travel further distances till it reaches the original height. So we are here. If the right side plane were ultimately made horizontal, that is, the slope is reduced to zero, the marble would continue to travel forever trying to reach the same height that it was released from the It was released from the unbalanced forces on the marble, in this case are zero. It thus suggests that an unbalanced external force is required to change the motion of the marble, but no net force is needed to sustain the uniform motion of the marble. In practical situations, it is difficult to achieve a zero unbalanced force. This is because of the presence of the frictional force acting opposite to the direction of motion. Just wait. Thus, in practice, the marble stops after traveling some distance. The effect of the frictional force may be minimized by using a smooth marble and a smooth plane and providing a lubricant on top of the planes. Ayush Shukla, I have noted down your request. Once I will be recording the Hindi video, a notification will definitely reach you. You can subscribe to have the recent notifications. Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of the objects. These three laws are known as Newton's laws of motion. The first law of motion is stated as an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied force. In other words, all objects resist a change in their state of motion in a qualitative way. The tendency of undisturbed objects to stay at rest or to keep moving with the same velocity is called inertia. That is why the first law of motion is also known as law of inertia. Certain experiences that we come across while traveling in a motor car can be explained on the basis of law of inertia. We tend to remain at rest with respect to the seat until the driver applies a braking force to stop the motor car. With the application of brakes, the car slows down, but our body tends to continue in the same state of motion because of its inertia. A sudden application of brakes may thus cause injury to us by impact. So here is this paragraph. Ayush Shukla, you can subscribe to my channel. In case I will be further doing the recording of Hindi, you can join in at that time. Galileo Galilei was born on 15 February 1564 in Pisa, Italy. Galileo, right from his childhood, had interest in mathematics and natural philosophy, but his father, Vincenzo Galilei, wanted him to become a medical doctor. Accordingly, Galileo enrolled himself for a medical degree at the University of Pisa in 1581, which he never completed because of his real interest in mathematics. In 1586, he wrote his first scientific book, The Little Balance, La Balentica, in which he described Archimedes' method of finding the relative densities or specific gravities of substances using a balance. In 1589, in a series of Essai de Montu, he presented his theories about falling objects using the inclined plane to slow down the rate of descent. In 1592, he was appointed professor of mathematics at the University of Padua in the Republic of Venice. Here he continued his observations on the theory of motion, and through his study of inclined planes and the pendulum, formulated the correct law for uniformly accelerated objects, that the distance the object move is proportional to the square of the time taken. Galileo was also a remarkable craftsman. He developed a series of telescopes whose observation performance was much better than those of other telescopes available during those days. Around 1640, he designed the first pendulum clock. In his book Starry Messenger on his astronomical discoveries, Galileo claimed to have seen mountains on the moon, the Milky Way, made up of tiny stars, and four small bodies of orbiting Jupiter. In his books Discourse on Floating Bodies and Letters on the Sunspots, he disclosed his observation of sunspots. Using Hits' own telescope and through his observations on Saturn and Venus, Galileo argued that all planets must orbit the sun and not the earth, contrary to what was believed at that time. So we are moving to the right side of the same page. or collision with the panels in front. Safety belts are worn to prevent such accidents. Safety belts exert a force on our body to make the forward motion slower. And opposite experience is encountered when we are standing in a bus and the bus begins to move suddenly. Now we tend to fall backward. This is because the sudden start of the bus brings motion to the bus as well as to our feet in contact with the floor of the bus. But the rest of our body opposes this motion because of its inertia. When a motor car makes a sharp turn at the high speed, we tend to get thrown to one side. This can again be explained on the basis of laws of inertia. We tend to continue in our straight line motion. When an unbalanced force is applied by the engine to change the direction of motion of the motor car, we slip to one side of the seat due to the inertia of our body. The fact body will remain at rest unless acted upon by an unbalanced force can be illustrated through the following activities. So, activity 8.1, make a pile of similar carom coins on a table as shown in figure 8.6. Next, attempt a sharp horizontal hit at the bottom of the pile using another carom coin of the striker. If the hit is strong enough, the bottom coins move out quickly. Once the lowest coin is removed, the inertia of other coins makes them fall vertically on the table. So figure 8.6 is only the carom coin at the bottom of the pile is removed when a fast moving carom coin for striker hits it. So let's move to this page now where activity 8.2 is written. Set a 5 rupee coin on a stiff card covering an empty glass tumbler standing on a table as shown in figure 8.7. Excuse me. Give the card a sharp horizontal flick with a finger. If we do it fast, then the card shoots away, allowing the coin to fall vertically into the glass tumbler due to its inertia. The inertia of the coin tries to maintain its state of rest even when the card flows off. So here figure 8.7 is given when the card is flicked with the finger, the coin placed over it falls in the tumbler. Next part, we are coming to this one, the activity. This is activity 8.3. Place a water-filled tumbler on a tray. Hold the tray and turn around as fast as you can. We observe that water spills. Why? Observe that a groove is provided in a saucer for placing the teacups. It prevents the cups from toppling over in case of sudden jerks. Figure now the next topic is 8.3, inertia and mass. All the example activities given so far illustrate that there is a resistance offered by an object to change its state of motion. If it is at rest, it tends to remain at rest. If it is moving, it tends to keep moving. This property of an object is called its inertia. Do all bodies have the same inertia? We know that it is easier to push an empty box than a moving box full of books. Similarly, if we kick a football, it flies away, but if we kick a stone of the same size with equal force, it hardly moves. We may, in fact, get an injury on our foot while doing so. Similarly, in activity 8.2, just wait. So here we go. 5 rupees coin. If we use 1 rupee coin, we find that a lesser force is required to perform the activity. A force that is just enough to cause a small car to pick up a large velocity will produce a negligible change in the motion of a train. This is because in comparison to the car, the train has a much lesser tendency to change its state of motion. Accordingly, we say that the train has more inertia than the car. Clearly, heavier or more massive objects often offer larger inertia. Quantitatively, the inertia of an object is measured by its mass. We may thus relate inertia and mass as follows. Inertia is a natural tendency of an object to resist a change in its state of motion or of rest. The mass of an object is a measure of its inertia. So here we come to the in-text questions. The first one is, which of the following has more inertia? A rubber ball and a stone of the same size. B, a bicycle and a train. C, a 5 rupee coin and 1 rupee coin. Question number two, in the following example, try to identify the number of times the velocity of the ball changes. So, a football player kicks a football to another player of his team who kicks the football towards the goal. The goalkeeper of the opposite team collects the football and kicks it towards a player of his own team. Also, identify the agent supplying the force in this case. Question number three, explain why some of the leaves may get detached from a tree if we vigorously shake its branch. Question number four, why do you fall in the forward direction when a moving bus brakes to a stop and fall backwards when it accelerates from rest? So next topic is 8.4, second law of motion. The first law of motion indicates that when an unbalanced external force acts on an object, its velocity changes. That is, an object gets an acceleration. We would now like to study how the acceleration of an object depends on the force applied to it and how we measure a force. Let us recount some observations from our everyday life. During the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast moving cricket ball hits a spectator, it may hurt him. A truck at rest does not require any attention when parked along a roadside, but a moving truck, even at speed as low as 5 meters per second, may kill a person standing in its path. A small mass, such as a bullet, may kill a person when fired from a gun. These observations suggest that the impact produced by the objects depends on its mass and velocity. Similarly, if an object to be accelerated, we know that greater force is required to give a greater velocity. To give a greater velocity. In other words, there appears to exist some quantity of importance that combines the object mass and its velocity. One such property called momentum was introduced by Newton. The momentum p of an object is defined as the product of its mass m and velocity v, that is p is equals to mv. Momentum has both direction and magnitude. Its direction is the same as that of velocity v. The SI unit of momentum is kilogram meter per second. Kilogram meter per second, since the application of an unbalanced force brings a change in the velocity of the object. It is therefore clear that a force also produces a change of momentum. Let us consider a situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter per second, which is sufficient to start an engine. If one or two persons give a sudden push unbalanced force to it, it hardly starts. So we are here at this line. A continuous push over some time results in the gradual acceleration of the car to its speed. It means that the change of momentum of the car is not determined by the magnitude of the force but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of an object depends on the time rate at which momentum is changed. The second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. So we are on the next heading, mathematical formulation of second law of motion. Suppose an object of mass M is moving around a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. The initial and final momentum of the object will be p1 is equals to mu and p2 is equals to mv respectively. The change in momentum is directly proportional to p2 minus p1, or mv minus mu or m bracket v minus u. The rate of change of momentum can also be written as directly proportional to m into v minus u upon t, or the applied force will become F is directly proportional to mv minus u by t. F is equals to km into v minus u upon t, so it will become kma. Here, A is directly proportional to v minus u by t is the acceleration, which is the rate of change of velocity. The quantity k is a constant of proportionality. The SI unit of masses and acceleration are kg and meter per second square respectively. The unit of force is so chosen that the value of a constant k becomes 1. For this, one unit of force is defined as the movement that produces an acceleration of 1 meter per second square in an object of 1 kg mass. That is, 1 unit of force is equals to kg in kilogram and 1 meter per second squared. Thus the value of k becomes 1 from equation 8.3. F is equals to m into a. The unit of force is kilogram meter per second square or Newton, which has the symbol of N. The second law of motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The second law of motion is often seen in action in our everyday life. Have you noticed that while catching a fast moving cricket ball, a fielder in the ground gradually pulls his hand backwards with the moving ball? In doing so, the fielder increases the time during which the high velocity of the moving ball decreases to zero. So thus the acceleration of the ball is decreased and therefore the impact of catching the fast moving ball, figure 8.8, is also reduced. If the ball is stopped suddenly, then the high velocity decreases to zero in a very short interval of time. Thus the rate of change of momentum of the ball will be large. Therefore a large force would have to be applied to for holding the catch that may hurt the palm of the fielder. In a high jump athletic event, the athletes are made to fall either on a cushion bed or on a sand bed. This is to increase the time of the athlete's fall to stop after making the jump. This decreases the rate of change of momentum and hence the forces also. Try to ponder how a karate player breaks the slab of ice with a single blow. So this is figure 8.8. A fielder pulls his hands gradually with the moving ball while holding the catch. Now we come on to this side, and this can be read as: the first law of motion can be mathematically stated from the mathematical expression for the second law of motion. Equation 8.4 is F is equals to ma. F will become mv minus u upon t. Ft will become mv minus mu. That is, when f is equals to 0, v is equals to u for whatever time t is taken. This means that the object will continue moving with uniform velocity u throughout the time t. If u is 0, then v will also be 0. That is, the object will remain at rest. Example 8.1. A constant force acts on an object of mass 5 kg for a duration of 2 seconds. It increases the object velocity from 3 meter per second to 7 meter per second. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? So answer can be read as: we have seen that u is 3 meter per second, v is 7 meter per second, t is 2 second, and m is 5 gram kilogram. So from equation 8.5, we have F is equals to mv minus u by t. Substitution of values in this relation gives F is equals to 5 kg. 7 meter per second minus 3 meter per second divided by 2 second gives 10 Newton. Now, if this force is applied for a duration of 5 seconds, so t is 5 seconds, then the final velocity can be calculated by rewriting equation 8.5 as v is equals to u plus ft by m. On substituting the values of u, f, m, and t, we get the final velocity, which is v is equals to 13 meter per second. Example 8.2. What would require a greater force, accelerating a 2 kg mass at 5 meter per second square or a 4 kg mass at 2 meter per second square? Solution. From equation 8.4, we have F is equals to ma. Here we have m 2 kg. As 5 meter per second, m2 is 4 kg. The above one was m1 and a1. Next is A2, 2 meter per second square. Thus, F1 is equals to M1 into A1. It will become 10 Newton after putting the values. Then we have F2 is equals to M2 A2. So it will be 4 into 2 is equals to 8 Newton. That means F1 is greater than F2. Thus, accelerating a 2 kg mass at 5 meter per second square would require a greater force. Example 8.3, a motor car is moving with a velocity of 108 km per hour and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kg. So solution can be read as initial velocity of the motor car U is 108 km per hour, which is 30 meter per second, and the final velocity of the motor car is V is equals to 0 meter per second. The total mass of the motor car along with its passenger is 1000 kg and the time taken to stop the motor car T is 4 seconds. Equation 8.5, we have the magnitude of the force F applied by the brakes as M V minus U by T. On substituting the values, we get F is equals to 1000 kg, 0 minus 30 in per second per 4 seconds. So the ultimately answer force will be coming as minus 7500 Newton. The negative sign tells us that the force is exerted by the brakes is opposite to the direction of the motion of the motor car. Example 8.4, a force of 5 Newton gives a mass m1 and acceleration of 10 meter per second square and a mass m2 and acceleration of 20 meter per second square. What acceleration would it give if both the masses were tied together? So solution is from equation 8.4, we have m1 is equals to f by a1 and m2 is f by a2. So acceleration a1 is 10 meter per second, a2 is 20, force is 5 Newton. Thus m1 can be calculated as 0.5 kg and m2 as 0.25 kg. If the two masses were tied together, the total mass m would be m is equals to zero point 0.5 plus 0.25 kilogram. It will give 0.75 kilogram. The acceleration A produced in the combined mass by the 5 Newton force would be A is equals to F by m means 5 by 0.75. That will give you 6.67. So it's a graph question. For example 8.5, the velocity time graph of the ball of mass 20 kg moving along a straight line on a long table is given in figure 8.9. So how much force does the table exert on the ball to bring it to the rest? So solution is the initial velocity of the ball is 20 centimeter per second. Due to the frictional force exerted by the table, the velocity of the ball decreases down to 0 in 10 seconds. Thus, U is 20 centimeter per second, V is 0 centimeter per second, and T is 10 seconds. Since the velocity time graph is a straight line, it is clear that the ball moves with a constant acceleration. The acceleration A is equals to V minus U by T. So A will become minus 0.02 meter per second square. So the force exerted on the ball F is equals to ma and it will be calculated as minus 0.0004 Newton. The negative sign implies that the frictional force exerted by the table is opposite to the direction of motion of the ball. 8.5, third law of motions. The first two laws of motion tell us how an applied force changes the motion and provide us with a method of determining the force. The third law of motion states that one object exerts a force on another object. The second object instantaneously exerts a force back on the first. So these two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. In the game of football, sometimes we, while looking at the football and trying to kick it in a greater force, collide with a player of opposite team. But feel hurt because each applies a force to the other. In other words, there is a pair of forces and not just one force. The two opposite forces are also known as action and reaction forces. Let's move on to this paragraph. Let us consider two spring balances connected together as shown in figure 8.10. The fixed end of balance B is attached with a rigid support like a wall. When a force is applied through the free end of a spring balance A, it is observed that both the spring balances show the same readings on their scales. It means that the force exerted by spring balance A on balance B is equal but opposite in the direction to the force exerted by the balance B and on balance A. Any of these two forces can be called an action and other is reaction. This gives us an alternative statement of the third law of motion, that is, to every action there is equal and opposite reaction. However, it may be remembered that the action and reaction always act on two different objects simultaneously. So figure 8.10, action and reaction forces are equal and opposite. Suppose you are standing at rest and intend to start walking on the road. You must accelerate it, and this requires a force in accordance with the second law of motion. What is this force? Is the muscular effort you exert on the road, is it on in the direction we intend to move? Now no, you push the road below backwards. The road exerts an equal and opposite force on your feet to make you move forward. It is important to note that even though the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitude. This is because each force acts on a different object that may have different masses. When the gun is fired, it exerts a forward force on the bullet. The bullet exerts equal and opposite force on the gun. This results in the recoil of the gun. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat. As the sailor jumps forward, the force on the boat moves it backward. Figure 8.11, forward force on the bullet and recoil of the gun. So activity 8.4, before that a diagram is given, figure 8.12. As the sailor jumps in forward condition, the boat moves backward. So activity 8.4 requests two children to stand on two separate cards as shown in figure 8.13. Give them a bag full of sand or some other heavy object. Ask them to play a game of catch with the bag. Does each of them experiences an instantaneous force as a result of throwing the sand back? You can paint a white line on cartwheels to observe the motion of the two carts when the children throw the bag towards each other. Now place two children on one cart and one on another cart. The second law of motion can be seen as this arrangement would show different accelerations of the same force. The cart shown in this activity can be constructed by using 12 millimeter and or 18 millimeter thick plywood board of about 50 by 100 centimeter with two pairs of hard ball bearing wheels. Skate wheels are good to use. Skateboards are not as effective because it is difficult to maintain straight line motion. Now we are done with the reading of this chapter. Let's finish with the summary also. So this is Force and Laws of Motion of class 9 Science NCRT. First law of motion: an object continues to be in a state of rest or of uniform motion along a straight line unless acted upon by an unbalanced force. The natural tendency of objects to resist a change in their state of rest or of uniform motion is called inertia. The mass of an object is a measure of its inertia. The SI unit is kilogram. Forces of friction always opposes motion of objects. Second law of motion: the rate of change of momentum of the object is proportional to the applied unbalanced force in the direction of the force. The SI unit of force is kilogram meter per second square. This is also known as Newton and is represented by the symbol N. A force of 1 Newton produces an acceleration of 1 meter per second square as an object of mass 1 kilogram. The momentum of an object is the product of its mass and velocity and has the same direction as that of the velocity. Its SI unit is kg meter per second. Third law of motion: to every action there is equal and opposite reaction and they act on two different bodies. So with this we are done with the reading of the chapter Force and Law of Motion. This is chapter number 8 of grade 9 Science NCRT. I hope you have liked the pronunciation. Whenever you'll be hearing the audio of this chapter, don't forget to share it with your friends. And thanks to the subscriber who has joined in the beginning and is there in the live till now. So stay connected and do hit the like button. You can comment in case you have any doubt and subscribe the channel Online Biology Tutorials to have the recent notifications. See you in next video. Thank you.